Hello viewers, good afternoon. Once again, we have a practice question here. In physics, practice question number 1. Now this practice question is actually under the Newton universal law of gravity. Now we have a question here that with diagram explain the relationship between acceleration due to gravity G on the Earth's surface and the universal gravitational constant G. Now, we didn't stop there. Further went on to say that, hence, if the radius of a planet is 1/4 and its mass 1/81st that of the Earth, calculate the acceleration due to gravity on the planet. If the acceleration due to gravity on the Earth's surface is 9.8 meters per second squared. Now, how do we solve this problem? To solve this problem, first and foremost, we should consider the Earth as a sphere. Now, let's assume this to be the Earth with center C. Now, this is the center of the Earth, and we should understand that it is a regular body, and the mass of the Earth is concentrated at the middle mass of the Earth. And the distance from the center to the circumference connotes the radius of the Earth. And here we have a body of mass on the surface of the Earth. So we are now considering a body of mass on the surface of the Earth, and this is the Earth. Now, from Newton's universal law of gravity, now also the mass of the body is concentrated at the middle. Mass of body, MB rather, mass of the body, concentrated at the center of that body. Now, according from Newton's universal law of gravity, we know that there exists a force of attraction between this body of mass and the Earth. So, according to the law, the force is directly proportional to the product of the masses, which is mass of the Earth and mass of the body. So, directly proportional to mass of the Earth, mass of the body. This same force is inversely proportional. Let me take it this way. That same force is inversely proportional to the square of their distance, and the distance here is the radius of the Earth. Square of the distance apart. Now, if we bring equation 1 and equation 2 together, we get a single equation, F directly proportional to mass of the Earth, mass of the body, all over radius of the Earth square. Now, if we remove sign of proportionality, we introduce a constant. So our F now will be equal to, the constant is now G. We have mass of the Earth, mass of the body, all over radius of the Earth square. Where G is the universal gravitational constant, this G we're looking at now. Now we want to see the relationship between this G and that acceleration due to gravity. Now also we should understand this body of mass, the weight of this object is acting vertically downward towards the center of the Earth. And the weight of an object is equal to mass of the object times acceleration due to gravity. So that is to say that the force of attraction between these two bodies of masses is equal to the weight of this object. So this force is now equal to the weight of the object, and weight, we have already said, is mass times acceleration. So we have a relationship that G, mass of Earth, mass of the body, all over radius of the Earth squared will be equal to weight of the body is mass of the body times acceleration due to gravity. From this expression, now this is an equality sign. Here, if we cross multiply, we have radius of the Earth squared, mass of the body times acceleration due to gravity equal to G, mass of the Earth, mass of the body. Now, from this point, now this is a point of emphasis, the acceleration due to gravity. So if I make acceleration due to gravity the subject of formula, we are going to have G, mass of the Earth, mass of the body, all over radius of the Earth squared times mass of the body. Mass of the body obviously will cancel that. So we are left with this equation, G equal to G mass of the Earth all over radius of the Earth squared. Now this expression here gives us the relationship between G, which is acceleration due to gravity, and the universal gravitational constant G. Remember, the universal gravitational constant G has a value of 6.67 times 10 raised to the power of minus 11, and the unit is Newton meter squared per kilogram squared. Now, this is the relationship between G and capital G. However, we still have a question to solve here. Hence, if the radius of a planet is 1/4 and its mass is 1/81st that of the Earth, we should calculate the acceleration due to gravity on the planet. If the acceleration due to gravity on the Earth's surface is 9.8 meters per second squared. How do we solve that? Now let's go on to solve that problem. Now, we have gotten this now. We should recall that acceleration due to gravity on the surface of the Earth is equal to G, mass of the Earth, all over radius of the Earth squared. So therefore, acceleration due to gravity on the planet will also be equal to universal gravitational constant, mass of the planet, divided by radius of the planet squared. But from what we have here now, this is our area of emphasis. We want to calculate the gravitational acceleration due to gravity on the planet. Now take a look at it. If you go back to the question said that the radius of a planet is 1/4. So therefore, radius of the planet is equal to radius of the Earth divided by 4. And it also went ahead to tell us that the mass is 1/81st that of the Earth. So it means that the mass of the planet also is equal to mass of the Earth divided by 81. Now we are going to substitute this into this expression here. To substitute these values into this equation, we have something like this. Take a look at it. The acceleration due to gravity on the planet now will be equal to, I have universal gravitational constant G, I have mass of the planet. Mass of the planet here, mass of the planet is equal to mass of the Earth divided by 81. So I will have mass of the Earth divided by 81 from what we have here now. Remember, this is now divided by radius of the planet squared. And radius of planet is equal to radius of the Earth divided by 4. So this is going to be radius of the Earth divided by 4. Remember, all raised to the power of 2, which is this square we have here now. Now we open up. So G is equal to 6.67 times 10 raised to the power of minus 11. You multiply that by mass of the Earth. And what is the approximate mass of the Earth? Mass of the Earth is 5.98 times 10 raised to the power of 24. That is the mass of the Earth. Now you divide by 81. Further divide this by radius of the Earth. And what's the approximate radius of the Earth? 6.38 times 10 raised to the power of 6 divided by 4. Remember, all squared. So we are supposed to have something like this. G per planet will be equal to 6.67 times 10 raised to the power minus 11 times 5.98 times 10 raised to the power of 24 divided by 81. Now look at it. Divided by 6.38 times 10 raised to the power of 6 divided by 4, all squared. Now here, let us add this together at once. All right. So we have it as 6.67 times 5.98, and that is giving us 6.67 6.67 times 5.98, that is giving us 39.886 times 10 raised to power minus 11 plus 24 divided by, here we have 81. At this point now, we still have divided by, what we have here now is 6.38 times 10 raised to the power of 6 all squared divided by 4. So here we have 39.87 times 10 raised to power this times this plus this is going to give us 13 times 10 raised to power of 13 divided by 81. Now this expression we have here divided by 6.38 times 10 raised to power of 6 squared divided by square of 4 is 16. So this expression is the same thing as 39.89 times 10 raised to the power of 13 divided by 81 times, when multiplication sign comes in, 16 comes up times 16 all over. Now let's take a look at this. 6.38 times 10 raised to the power of 6 squared, that is giving us 4.07 times 10 raised to the power of 13. So at this point now we multiply. So if we multiply 16 times 39.89, 16 times 39.89, that is going to give us 638.24. Then times 10 raised to the power of 13. Divide by 81 times 4.07. So 81 times 4.07, that is giving us 329.67 times 10 raised to the power of 13. Now you can see what we have here now. So here now we take this. So this is now going to give us 638.24 divided by this. 638.24 divided by 329.67. That is giving us 1.94 times 10 raised to the power of 13 minus 13. Remember, law of indices. When it comes up here, this is the same thing as the bases are the same, the powers are also the same. So it's the same thing as 13 coming here becomes minus 13. 13 minus 13, which is 10 raised to the power of 0, and that is equal to 1. So therefore, the acceleration due to gravity on the planet will be equal to 1.94 meters per second squared. That is so it means that from what we have there, the acceleration due to gravity on the planet is drastically reduced, 1.94 meters per second squared, compared to what we have on the surface of the earth, which is 9.8 meters per second squared. So this is the solution to that practice problem. Hope it got to you in the right state of mind and it is well understood. Thank you very much. Until we meet again next episode. Thank you.